Welcome back, students. In the previous lecture we have talked about derivation of the Biot-Savart law, and we tried to calculate magnetic field intensity H bar due to a finite current carrying conductor with a current I, and we came to this particular thing. I will just repeat it once again so that it will become easier for you to understand. So you already know the R bar is calculated as rho A rho bar minus Z A Z bar. That is clear. Now DL bar cross R bar, I will just explain it once again. See, DL bar is dz az bar. Why it is dz az bar? Because line charge is along line current charge current distribution is along z axis. So DL bar I can write it as dz az bar, and I want to take off this dz az bar cross with rho A rho bar minus Z az bar. So dz into rho, I will just calculate this dz into rho. So it is rho dz az bar cross A rho bar. By the property of the cross product, we know az cross A rho will be A phi bar, and I will get rho dz A phi bar, whereas dz az bar into Z az bar, so az bar cross az bar will be equal to 0. And finally we got DL bar cross R bar as rho dz A phi bar, and we put these values I rho dz upon 4 pi rho square plus z square raised to 3 by 2 A phi bar. And I need to solve this integration by the substitution method, where I can put a substitution as rho equal to z cot alpha. If I put z equal to rho cot alpha, dz equal to minus rho cosec square alpha d alpha. We know the limits of alpha are running from alpha 1 to alpha 2. Then what we did, we have put rho square cosec square alpha. Why rho square cosec square alpha? Because dz is rho cosec square alpha, and already rho is there. So it will be minus rho square cosec square alpha in the numerator, whereas in the denominator we will get 4 pi square rho square plus z, we have put rho cot alpha, so rho square cot square alpha. So rho square raised to 3 by 2, we can take it outside the sign of this bracket, and it will come to be rho cube, and 1 plus cot square alpha is cosec square alpha. So minus I upon 4 pi, I have corrected this in the previous video also, minus I upon 4 pi, integration running from alpha 1 to alpha 2, rho square cosec square alpha divided by rho cube cosec cube alpha d alpha into A phi bar. So if this integration is to be solved, let's first of all make certain simplification. So rho square upon rho cube, it come out to be minus I upon 4 pi rho A phi bar integration alpha integration running from alpha 1 to alpha 2 sin alpha d alpha. A phi bar is also constant, we have taken it outside, and I finally got this expression. This is a very important expression, I upon 4 pi rho cos alpha 2 minus cos alpha 1 A phi bar. Equation 3 is valid for any straight filamentary conductor of finite length. This is very important because in the previous lecture we have talked about this is only applicable in case of finite length of the current carrying conductor. So as a special case we can derive for infinite length current carrying conductor, but right now this is applicable in case of finite length current carrying conductor. So I hope you have just understood this formula, so that we can proceed for this next cases. I am having this marker and I need to draw it by the touchpad, so sometimes it becomes difficult for me to draw, so just cooperate. So this is the final expression, H bar is equal to I upon 4 pi rho cos alpha 2 minus cos alpha 1 A phi bar. So let's try it out with certain cases when a conductor is a semi-infinite. What I mean to say by semi-infinite, if let's say these are the axes which I want to draw, x-axis, y-axis and z-axis, and the conductor, let's say this conductor I want to draw it by a red color line, and it is extending from 0 till infinity. So coordinates are 0 0 0 to infinity infinity, so it is semi-infinite. So if it is from minus infinity to plus infinity, is completely infinite. When it is semi-infinite, so the coordinates will be what? The coordinate of point A, let's say this is point A, the coordinates of point A will be 0 0 0, and coordinates of point B will be 0 0 infinity, since it is along z axis, so 0 0 infinity. So let's say this is once again a point of interest where I need to calculate. I will draw it by these two lines. I know alpha 1 and alpha 2. Alpha 1 should be taken as outer angle, alpha 2 will be taken as inner angle, and if I try to calculate, okay, if I go on increasing, this alpha 2 tends to be 0, yes or no, because this is shrinking. As this is extending, once again this alpha 2 is going to shrink, and finally alpha 2 I will get it as 0, whereas alpha 1 I am going to get it as 90. Listen to me carefully. Alpha 2 I am going to get it as 90 degrees, since it is directly finite, semi-infinite, the angle made by this point A with the point P is 90 degree. So if I put these both things here, so alpha 2, which is the inner angle, as 0, so cos 0 is 1, minus cos alpha 1, cos 90 as what? Cos 90 as 0. So it is I upon 4 pi rho, the final expression I will get, I upon 4 pi rho A phi bar. So this equation is applicable for the case of semi-infinite current distribution. If I want to talk about finite, infinite current distribution, that means it will be 0 0 minus infinity to 0 0 infinity. If I want to draw once again, let's say these are the axes x, y and z axis, and I will now try to draw this current distribution something like this, which is infinite. So it is extending from minus infinity to plus infinity. So as it is along z axis, coordinates will be 0 0 minus infinity and 0 0 plus infinity. So let's say this is a point P where this is a point of interest. So I will draw this. Let's say this is point A, this is point B. So this is angle. I know I need to calculate alpha 1 as outer angle and alpha 2 as inner angle. So once again, since it is infinite, alpha 2, as in the earlier case, it is going to tend to 0, but alpha 1 is going to tend towards almost 180 degree. So alpha 1 is 180 degree, alpha 2 is 0. You just try to imagine this is an infinite line charge extending from infinity to minus infinity. Alpha 2 is the inner angle, it is going to tend to 0, and alpha 2 tends towards 180 degree. So if I put alpha 1 equal to 180 degree, here alpha 1 as 180, cos 180, you already know cos 180 is minus 1, minus of minus 1 is plus 1, cos alpha 2 is 0, so 1 plus plus 1, so it is 2, so 2 get cancelled with this 4, so I upon 4 pi rho A phi bar. So this is H bar for infinite current distribution. So these are two special cases of DH bar. So sometimes in the examination this question can be asked, that find H bar due to finite current carrying conductor, and what will be the equation for H bar, that is magnetic field intensity, if it is a infinite current distribution. So either of these two cases you can solve it. So at the final, A phi bar, how we have calculated A phi bar? See, previously A phi bar we have calculated. I will take you back here. See how we have got this A phi bar. A phi bar is the cross product of, this is dz az bar. It was cross product of az cross arrow. But why it is az? It can be anything. If it is line charges along A phi, it will be A phi. If a line current is along arrow, it will be arrow. But why it is az? Since the current distribution was, we have assumed it to be along z axis, that's why we have taken it something like that. So let's try to understand how to calculate. So this is a hint that you required for solving the numerical A phi bar. So try to understand one basic formula for calculation of A phi bar. Now you have one equation of H bar. H bar is equal to I upon 4 pi rho cos alpha 2 minus cos alpha 1 A phi bar. What is that A phi bar we need to calculate? So A phi bar is equal to AL bar cross arrow bar. What is this AL bar? AL bar is unit vector along the current carrying conductor. So unit vector along the current carrying length of the conductor. Cross arrow bar is what? Unit vector along perpendicular line from the field point. So remember these two things, AL bar cross arrow bar. So A phi bar is calculated by AL bar cross arrow bar. So AL bar is the unit vector along the line current. So if line current is along x axis, it will be AX bar. If it is along y axis, AY bar. If it is along z, AZ. Similarly, if it is along rho, arrow bar. If it is along phi, it is A phi bar. If it is along z, AZ bar. Crossed with this arrow bar, this is also important. This arrow bar indicates to me the unit vector perpendicular along the perpendicular line from field point. So if I have taken this line charge, just see an example. If this is a line charge along z axis, so arrow bar will be unit vector in the perpendicular direction. So we have gone through certain numericals of the line charge distribution in the Gauss law. Similar concept you need to apply for calculating arrow bar. Once you calculate arrow bar, it is just you need to take a cross product between AL bar and cross arrow bar to calculate the certain things. So in the next lecture, or I will first of all provide you one numerical, solved numerical in the PDF note. Just try to go through it. Once you understand that, it becomes easier for you to just elaborate this, and if you don't understand, we will carry on that discussion in the live sessions of our electromagnetics. So don't worry about that, we will try to solve it by giving certain time. So till then, happy learning. That's it. Thank you very much.